Hello and welcome to the lecture. So, in this lecture, we will start with the question. So, the question is, we have which among the following is the strongest Lewis acid? Now, we have here BF, we have BCl, and we have BBr. Now here in this case, boron, it is having an empty orbital, and fluorine, it is also having empty orbital. Here boron, fluorine, is having an orbital having lone pair electron. Similarly, we have here p orbital which is empty, and we have orbital of chlorine having lone pair. Similarly, here we have bromine, it is having empty orbital, and bromine, it is having electron density it is having a lone pair. Now what happens here is that the back bonding will occur from the filled 2p orbital of fluorine to the empty orbital of bromine. So here back bonding will occur. Similarly, here the back bonding will occur from chlorine to the empty orbital of bromine, similar to boron. Similarly, here the electron density will be from the orbital of boron to the empty orbital of orbital of boron. Now here this is the back bonding, it is between 2p and 2p. Here the back bonding is between 2p and 3p, and here the back bonding is between 2p and 4p. So as we know that because of a similar size of 2p and 2p, here the back bonding will be highest. Here because of 2p and 3p interaction, it will have less back bonding, and here the back bonding will be least back bonding. This will have high back bonding. So it means that this orbital of boron, it will have high electron density. It means that it will be least Lewis acid. Means it has high electron density in 2p orbital of boron. It means that it will have least tendency to accept the electron. So this orbital of boron, it is having high electron density, so it will have least Lewis acidity. Similarly, here it is also filled, it is also having back bonding, but this back bonding, it will be less, and this back bonding, it will be least. It means that this will have least electron density, that is in this boron, because of 2p and 4p interaction, this orbital of boron, it will have less electron density, but it means that it will have high tendency to accept the electron. So we can say that BBr3, it is having high Lewis acidity. It will be followed by BCl3 followed by BF3. So among the following species, BBr3, it will have high tendency to accept the electron. Why? Because it has least back bonding. Similarly, BCl, it will have the electron it will be followed, and BF3, it will have least Lewis acidity. Now the second part of the question is, we have boron and we have attached with this normal butane 3, and we have boron, it is having tertiary butane attached. Now here, since normal butane, it is having less steric hindrance, and tertiary butane, it is having high steric hindrance. High steric hindrance. It means that when a species that is having high electron density, it will try to attach itself on this boron, it will feel no steric hindrance. It will feel less steric hindrance. But if the same group, it will try to attach itself to this boron, it will feel high steric hindrance. So it means that this boron having normal butane attached, it will have high tendency to accept the electron. So it will have high tendency. It will be a strong Lewis acidity. It will have high strong acidity. It will be followed by the species having tertiary butane. So this is the Lewis acidity order. This is the Lewis acidity order. Now let us try to understand another concept. This concept is about Lewis acidity, and this concept is about concept of hard acid and hard base. So we have the concept of hard acids and hard bases. Hard bases. Similarly, we have soft acids and we have soft bases. Now first of all, let us have a look at hard Lewis acids. Hard Lewis acids. Now hard Lewis acids, we have the examples like BX3, that is boron trihalides. So we have, suppose BF3, it is a hard Lewis acid. Similarly, we have BCl3, we have BBr3, and we have Bi3. Now what happens here? We have here BF interactions. Here we have BCl interactions, and here we have BBr interaction, and here we have Bi interactions. Now here we have the interaction between lobes, between the p orbital, that is 2p interactions. Here we have 2p3p interactions. Here we had 2p4p interaction, and here